Okay, so we're going to move on to section 3, but the handout I gave to you, or handouts, meant to be one handout, but I apparently didn't push the one side to two sides or something. I know what I did now. So the first side, well, the one that says summary of tests for series. So basically we're going through all these tests. So we've done the nth term test, geometric series test, telescoping series, well, we're going to do the P series and the integral test today. The one that turns out in the long run to be the most important is the ratio test, which we'll get to, I guess, Thursday. And the whole purpose of this, if you go to the second page, is you'll see power series for elementary functions. So we've seen some of these before, like the sine of x is x minus x cubed over 3 factorial. And if you look at the right-hand side, it has a column called interval of convergence right there. And what those are the values of x where the series converge. So for the ones that we're usually most interested in, e to the x, sine x, cosine x, those are good for all values of x. But some of the other ones have limited domains where they are where they converge. So the whole idea for these formulas is to figure out whether these series converge or not, and for what values of x they do converge, if they do converge. Okay, so here's the integral test. It says if f is a positive, continuous, and decreasing function for x greater than or equal to 1, and the nth term of the series can be represented as a function, then if the series, the summation from n equals 1 to infinity of a sub n, and the integral of f of x dx from 1 to infinity, if either both converge or both diverge. So basically what we're going to do is we're going to look at the nth term, the equation for the nth term of the series, and if we can substitute x for n, and then we can evaluate the integral. If the integral converges, then the series converges. And if the integral diverges, then the series diverges. And it kind of makes sense because, you know, what are these two represent? Let me see if I have this down on my next page or whether I need to draw it. So put this over here. Yeah, no, okay. So let me explain what's going on. Because if you think about a series, let's say we have, we'll just make one up here. Let's say 1 over n, from n equals 1 to infinity. And we plot that. So let's say for n equals 1, you get 1. So this is 1. For n equals 2, 1. For n equals 2, you'd get 1/2. And for n equals 3, you'd get 1/3. And for n equals 4, you'd get 1/4. So that's how we would represent the series, is just dots. But if we were to take them and make them into rectangles, so if we made a rectangle like this, and then we made a rectangle like that, and I'm making them the height of the value of the series, the nth term of the series, finding the area under these rectangles where the width of the rectangle is 1 and the height is the value of the series at the particular values of n, that you would get the same answer. because they're all a width of 1 unit, the area is going to be the same as the value of the nth term in the sequence in the series. So if I did this, how do you represent this? Let me just write it out if you still don't believe me. So if I do that of 1 over n, that's going to be equal to 1 plus 1/2 plus 1/3 plus 1/4. We could say the area of the rectangles is equal to 1 times 1 plus 1/2 times 1 plus 1/3 times 1, etc. So because the width is 1, you get the same answer, whether you multiply by the width. But by multiplying by this width of 1 unit, I'm creating an area instead of just adding numbers together. Now if I plot the function, so the function looks something like this, except for the function, you connect the lines together, the points together. So I was going to do a red line here. So you come through like this, and what we're doing there is we're finding this area. And you might say, well, it looks like the area under the red curve is less than the area under the rectangles, and that's true, but there's two things. One is if the red curve converges, then definitely the area underneath, no, that's not necessarily true. So I can't use that argument. But I can use the argument that the reason the function converges, the integral of the function, so what function are we talking about? We're talking about, so the corresponding function that we would evaluate is the integral from 1 to infinity of 1 over x dx. And it turns actually, we know that diverges. And it's not because my rectangles are sticking out the top, it's just because we know it diverges because we did it back in chapter 8, section 8. But the whole idea there, whether something converges or diverges, is how quickly the function approaches the x-axis. And the same can be said about the values of the terms in the series. So if that approaches the x-axis quickly enough, then the same kind of phenomenon occurs for a series. So that's kind of why it works. So let's use this, use the integral test to determine the convergence or divergence of the following. So what we would do is we would say, well, let's replace this series with the integral from 1 to infinity of the natural log of x divided by x squared dx. And then we'll evaluate that integral, and if it diverges, then the series diverges. If it converges, then the series converges. So now how am I going to do, let me remember how to do this. Anybody have any idea how I might solve this problem? Think about the test tomorrow. It's one of those techniques. Yeah, it almost has to be that because all the other ones involve trig functions except partial fractions. So yeah, it involves, so what we do is we would let u equal the natural log of x and dv equal 1 over x squared dx, or that be x to the minus 2 dx. So we take the derivative of that, so we get du is equal to 1 over x dx. v is equal to x to the minus 1 divided by negative 1, which is equal to negative 1 over x. Integration by parts says the integral of u dv is uv minus the integral of v du. So for our case, u is the natural log of x, v is negative 1 over x. Then we subtract the integral of v du. V is negative 1 over x. Du is equal to 1 over x dx. So you get negative 1 over x, natural log of x, plus the integral of 1 over x squared dx. Well, I know what that is. I just did it here, right? So you get negative 1 over x, natural log of x, minus 1 over x plus c. Okay, so that's the indefinite integral. So now we have to evaluate that. So let's plug it back into we're going to plug it back in here now. So it would be negative 1 over x, natural log of x, minus 1 over x, evaluated between 1 and infinity. Now this is actually where we're going to have to use L'Hopital's rule again, because if I plug in infinity, so I probably should go back and rewrite this as the limit, since I should have done that in the first place, really. I was a bad boy. So just don't do this. Okay, so at least I realized I was a bad boy. Okay, so let's write it. Limit as b goes to infinity of the integral. It's easy to do. Okay. Okay, so we're doing natural log of x over x dx. Okay, so then we go limit as b goes to infinity of, so we integrate it. Okay, now we plug in what we just had. So we get negative 1 over x, natural log of x, minus 1 over x, evaluated between 1 and b. And then we plug in the limits. So we get the limits of integration, not taking the limit. So you'd have 1 over b times the natural log of b minus 1 over b. So that's evaluating at the upper limit. Minus, so you subtract the lower limit, which would be negative 1 over 1 times the natural log of 1 minus 1, 1 over 1. Well, the natural log of 1 is 0, so that term drops out. You can see as b goes to infinity, this term is going to go to 0. Right now, all I have is this last term, which is going to be positive 1. So the only thing I have to do is evaluate what that thing is. So you'd have to use L'Hopital's rule. So I'm going to do that separately. So take the limit as b goes to infinity of negative the natural log of b over b. So just thinking about it before we use L'Hopital's rule, does anybody have any idea what that might be? Usually, a lot of times with L'Hopital's rule, it's either 0 or it's undefined. And remember, what you look at is the relative behavior of each one of those functions, the natural log of b versus b. So y equals b would look something like that. The natural log of b would look like that. So what's happening is that the natural log of b is going to be getting smaller relative to b. So that means that should go to 0. Okay, without using L'Hopital's rule, but we're going to use L'Hopital's rule to prove that it's true, but I'm sure that's the answers. Okay, so that's going to be, because normally you'd get infinity over infinity, which is indeterminate. So we take the first derivative of the numerator and the denominator. So the first derivative of that would be 1 over b. The derivative of b would be 1. And you can see now it's not indeterminate anymore, but if I plug in b equal infinity, I get that, which is 0. So L'Hopital's rule says that's also 0. So the answer is 1. The integral, the answer to this question, wherever the integral from 1 to infinity of the natural log of x over x squared dx is 1. So we don't really care what the number is. We just care that it's a number. So what we can do, once you have made that observation, you can say, how do we want to say this? Since the series summation from n equals 1 to infinity of the natural log of n over n squared can be evaluated using the integral test and the integral from 1 to infinity of the natural log of x divided by x squared dx converges. The series also converges. It doesn't converge to 1. This test doesn't tell you what it converges to. It's just telling you that it converges. I think if we tried to evaluate this series, I don't think it would equal 1. We could try it and see what happens. We did that last week. Let's just do it for the heck of it. So if I go to Excel, my way for evaluating all series. So we'll have n, we'll have a sub n, we'll have the sum, and so we'll start with n equal 1, 2, so a sub n is equal to the natural log of n divided by n squared. So that's the sum. And okay, so we'll copy that down. And then that's equal to that plus that. And then we just copy that down however far we're going to go. So it looks like it's 0.83 something. Let's see how. We'll keep going here. Let's make it a couple hundred terms. I'm just curious how close to 1 it will be. We may not be able to tell. Yeah, so it looks like it might be a little less than 1, but it could be 1. I don't know. Oh yeah. So we should have, don't forget, just to remind me, don't forget to check that the integral, that the function is positive, continuous, and decreasing. So we probably should plot the function just to confirm that. So if we plot the function using our graphing program, and we plot the natural log of x divided by x squared, so that's what it looks like. And if I zoom out in the x direction, you can see it's positive, it's continuous, and it's decreasing. So it does satisfy those requirements. Oh. Okay, so here's another one. So I'm going to let you, I'm going to see if you can remember how to do this. So what you do is you do the integral from 1 to infinity of 2x divided by x squared plus 1 dx. And you don't have to use L'Hopital's rule with this one, so it's easier. So you'll have to use u substitution. The denominator is u, the numerator is du, okay, and then you'll I guess the question, it is a definite integral, so do you also you have to do this limit thing, which I'm as bad as the next guy. So don't forget to do that. Take the limit as b goes to infinity, 1 to b of 2x over x squared plus 1 dx. And let u equal x squared plus 1. So did anybody have any unusual Easter dinners? Great. What do you have any interesting Easter dinners since you're Filipino? No.
We had dinner on Saturday. We just had ham, green beans, mac and cheese, the usual.
Oh, sounds.
And we had, well, I call it corn pudding, and my family calls it corn casserole. And the people I work with, they call it cornbread. And so we had like a debate about it.
What it was? I mean, corn pudding is we make corn pudding, and it's more like
Yeah, it's not corn
like
bread.
a pudding kind of thing.
Bread.
It's bread. If it's flaky, it's
just
bread.
like if it just, like,
Yeah, right.
That's not what it is. So I thought about it.
Yeah. Anybody else have any interesting things for Easter dinner? Non-traditional?
We had orange Jello.
Orange Jello. That was it, huh? No, just kidding. Dessert. Yeah, we had Martha made. It was kind of weird. We had crab cakes. So Martha cooked the crab legs and picked all the crab out of the crab legs and made crab cakes out of it. Potato salad and asparagus. That is kind of It was good though. It was good. So one of the questions here may be, do I need to change the limits of integration? And yeah, possibly you do, if you want to, or you can plug it back in. So I'll do it where you change the limits of integration. You can. So we'll say when x equals 1, u equals 1 squared plus 1, which is 2. And when x equals b, u equals b squared plus 1, which is just b squared plus 1. Okay. Or you could go through this and then substitute back in. So let's see. So we're going to have the limit as b goes to infinity of the integral from 2 to b squared plus 1 of du over u. And the integral of du over u is the natural log is equal to the natural log of the absolute value of u evaluated between 2 and b squared plus 1. So that is the limit as b goes to infinity of the natural log, the absolute value of b squared plus 1 minus the natural log of the absolute value of 2. But you can see as b goes to infinity, b squared plus 1 goes to infinity. The natural log of b squared plus 1 goes to infinity. So the whole thing goes to infinity. Therefore, it diverges. So because the integral diverges, then the series diverges. So therefore, since the integral from 1 to infinity of 2x divided by x squared plus 1 dx diverges, the series, the summation from n equals 1 to infinity of 2n over n squared plus 1 also diverges. Okay. So we've had an example of each case. We had the first one was where the integral converged, therefore the series converged. The second case, the integral diverged, so the series diverged. Okie dokie. Okay, so P series, there are, the harmonic series is a special case of a P series where P is equal to 1. But a P series, instead of having something raised to the n power, which I think we did for the geometric series. Remember, the geometric series had r to the n, or 1 over r to the, it was r to the n, a times r to the n. In this case, n is the base instead of the exponent. And p can be any value from 0 to infinity. And the question is, there's going to be some rules that relate to p to tell us whether the series converges or diverges. So they all have the same form, 1 to the p power, 2 to the p power, 3 to the p power. If p is equal to 1, then it becomes a harmonic series. So the rule is here, convergence for the P series. It converges if P is greater than 1, and it diverges if P is between 0 and 1. Well, not equal to 0, because then that wouldn't work out, but it has to be greater than 0. Less than 1, it diverges. So again, all you have to do in this case, if you look at your sheet for P series, it says P series. It gives you the convergence criterion. That's all that is. Yeah. You just have to identify whether something is a P series or not. Now, later on, we'll find out that there are cases where they're not exactly like a P series, but we have a test which is called the direct comparison test near the bottom. And if you can simplify it down to a P series, then by ignoring certain terms, then you can still use the P series test for a more complicated series than what we're showing here. But the first thing here is just to recognize something as a P series. Use theorem 911 to determine the convergence of the following. Okay, so that's just telling us the instructions for doing the next bunch of problems. So that may not initially look like a P series. Sometimes they don't. But if you rewrite this as a fractional exponent, so you get 1 over n to the 1/5 power. So the 5th root is to the... So now you can see, now it looks like a P series. Aha. I don't know how to say aha. Is that right? I don't know. So once you recognize the P series, then you just go back and say, what's the rule again? I forgot. Okay. It converges if P is greater than 1. Okay. So all you have to do is say, aha, this is a P series. Hence, according to the convergence criteria for the P-series tests So according to the convergence criteria, which says that if P is between 0 and 1, then the series, therefore, I guess I'll put therefore, the series diverges. Now in this case, they give you one that you have to look at and see if you can figure out what the actual equation form for the series is. And so let's see if I can think of let's go back to look at a P-series again. So that's 1 over n to the P. Okay. So that looks squared, cubed. Well, it's 2 squared, 3 squared, 4 squared. So it looks like it's going to be n to the p somehow or another, right? Is it just where p is 2? Yeah, because it's squared. Right? Does that work out? So when n equals 1, you get 1 over 1 squared, which is that. When n equals 2, you get 1 over 4 squared. So that works out. So all I did there was I realized that I have the same, I'm raising a number in the denominator to the same power. It's just an increasing power. So once you get it in the form that is recognizable as a P-series, we could do the same thing. Aha. Just copy that again. You don't have to put the aha in there. And this one's just to show you that the exponent doesn't have to be an integer. It can be, or it doesn't have to be a rational number. So does that converge or diverge? Using the convergence criteria for the P-series. Yeah, it converges because pi is greater than 1. So basically the same thing. I'll leave the aha off. Say this is a P-series, hence according I think that's it for P-series. Maybe not. We'll go ahead and assign the homework for this section. Yeah, I was just looking at this one. Oh, I have to come back to that one. Actually, I think I know what the answer to that one is. Because it kind of looks like the one we just did when we were looking at the integral test. I don't think this is an integral test question. Because we did the same problem where p was squared, right? P was 2. If we look back at the problem that we did just a little while ago, I'll come back to this in a second in case you haven't got them all answered, all written down yet. But if you remember back here, this first problem we did was basically a special case where p is equal to 2. And we saw that with p equal to 2 that it converged. And I think what we'd find out is that it's probably the same kind of criteria. If p is greater than 1, it converges, and if p is less than 1, between 1 and 0, it converges. But I'm going to skip over that for right now. We're going to move to the next section. Section 4. Okay, let's see what section 4 is about. Section 4 is comparisons. So we're going to skip over the tests involving ratio and root, and we're going to go to direct comparison and limit comparison tests. And then we'll come back in section 5 and talk about, I think section 5 actually is about alternating series, and section 6 is about ratios. So here are the tests. It says for the direct comparison test that you look at two different series. There's a series A sub n and a series B sub n. And what it's saying is that if for all n the series A sub n, if it says if B sub n converges and A sub n is always less than B sub n, then A sub n has to converge. Likewise, if A sub n diverges, then B sub n diverges because of the size, the relative size. So if this one diverges, but this series is always bigger than that one, it makes sense that this one diverges. Also, like again here, if you have a series where every term is larger than another series, and this series converges, then the smaller one, the one you add smaller terms together, has to converge. So it just makes sense. I don't know if you need even have a proof for this thing. And the reason this works out is because you might be able to make A sub n be a series that you know how to use a previous test. So if you can come up with a function A sub n, you'll be given B sub n. But if you can come up with a series A sub n that can be, this question can be answered by using some of the previous convergence criteria, then you can use that to prove that this is also converges. So here is our first example. Use the direct comparison test to determine convergence or divergence. So this is B sub n. No, actually this is A sub n, sorry. So we would say in this case A sub n is equal to 1 over n squared plus 1. So this is equal to the summation from n equals 1 to infinity of A sub n. Now what we're going to do is we're going to choose b sub n to be 1 over n squared. And because here I add 1, I'm always adding 1 to the denominator, this is always going to be smaller than that. Now how do you prove that? There's a couple of different ways to prove that. So I'll say this is true. It's true that a sub n, for one thing, is always positive, and it's always going to be less than b sub n. So there's one way would be just to make up a table of the two series and compare the values and convince yourself that it's always going to be the case. So I'm going to make a table with 3 columns instead of 2 columns. So this will be n. This will be 1 over n squared plus 1. This will be 1 over n squared. So let's just do this column first. So you get 1 over 1 squared, which is 1. You get 1 over 2 squared, which is 1/4. You get 1 over 3 squared, which is 1/9. In the second column, you'd have 1 over 1 squared plus 1, which would be 1/2. 1 over 2 squared plus 1, which would be 1/5. And then you get 1 over 3 squared plus 1, which would be 1/10. And you can see that 1/2 is less than 1, 1/5 is less than 1/4, 1/10 is less than 1/9. And there's, because of this adding this 1, this denominator is always going to be 1 greater than this, and therefore this number is always going to be less. So that would be one way to prove that it's true. The second way is you can take these two and say 1 over n squared plus 1 is less than 1 over n squared, and then figure out the values for n where that's true. So you could cross multiply. So you get n squared is going to be less than n squared plus 1. And then you could subtract n squared from both sides, and you'd say 0 is less than 1, always. Okay. So because you end up with that result from this initial assumption, this is true whenever this is true. Well, this is true all the time, so this has to be true all the time. So that's how you would do it algebraically. So now once you have proved that the a sub n is always less than b sub n, then you look at the convergence of this. So what we can say is that the summation from n equals 1 to infinity of b sub n, which is the summation from n equals 1 to infinity of 1 over n squared, is a p-series where p equals 2. So since this is a p-series and p-series converge when p is greater than 1, then the summation from n equals 1 to infinity of 1 over n squared converges. So we're proving this one converges according to the p-series, but then we have to use the direct comparison test to prove then using the direct comparison test, since this is true and the summation of b sub n as n goes from 1 to infinity converges, the original series that we were looking at, the summation of a sub n from n equals 1 to infinity, which is the summation from n equals 1 to infinity of 1 over n squared plus 1 also converges. So the direct comparison test involves a convergence test within a convergence test. You always find a simpler function. B sub n is always something that is simpler that I can evaluate the convergence of. So there's two requirements for B sub n. One is it's something I can evaluate using one of the other convergence tests. And secondly is that it's always greater than the one that I was originally interested in. With those two things being satisfied, then I can look at the convergence of this. And if this converges, then I know that this converges by the convergence criteria of the direct comparison test. Okay, let's see what else we got here. So this is a similar kind of thing. What you would do, you'd have a sub n is going to be 3 to the n over 4 to the n plus 5, and you would let b sub n equal to 3 to the n over 4 to the n, or 3 over 4 to the n. So what I've done is I've dropped that 5 term, and then I've grouped the two terms together because they have the same exponent. And that's not a p-series, but that's a geometric series. So the idea here would be to find the, well, first you got to figure out if a sub n is always less than b sub n. In this case, I'm trying to think if you can do that using, it's not going to be quite as easy as the previous one doing it algebraically, but so I probably would do it something like this. I'd set up a table, try a couple of values of n, and there's no reason to believe that if it works, if this inequality applies for the first few values, it's going to change for the subsequent values. So let's just do that. We're going to set up our 3-column table. We'll have n. We'll have 3 to the n over 4 to the n plus 5, and we'll have 3 to the n over 4 to the n. And we start with n equals 0 in this case instead of n equals 1. So we'd get 3 to the 0 over 4 to the 0 plus 5, and that's 1 over 6, that's 1/6. And here we'd have 3/4 to the 0, which would be 1. So 1/6 is less than 1. And then we do 3 to the first power divided by 4 to the first power plus 5. So that's going to be 3 over 9, which is 1/3. And if we take this, we get 3 over 4 raised to the first power, which is 3/4. So that's still true. We'll do one more. 3 squared over 4 squared plus 5, and 3 squared over 4 squared. So that's going to be 9/16. And here we're going to have 9 over 21. So it looks like I can convince myself that's going to work out, because this one, the only difference is you're going to add 5 to the denominator. So these are always going to be the same, except this one's going to have a larger denominator. And so this is always going to be less than that. So that does satisfy the requirements for the direct comparison test. And then all you have to do is look at the convergence criteria for the geometric series. So you go to your paper and you look at the convergence criteria for the geometric series, and it says if the absolute value of r, which is 3/4, is less than 1, then it converges. So we'll write that out in full form next time, but this series, b sub n, summation of b sub n as n goes from 0 to infinity, converges because the common ratio is less than 1. So this converges, and because this is always less than that, this also converges. So like I said, we'll write out all the details next time.